All right, so in this section, we are going over 3.3 differentiation rules. So we've already gone over the section 3.2, which is on the derivative function, and we figured out how to find the derivative function using the limit definition of the derivative. And today we're going to simplify our derivations quite a bit with these differentiation rules. Okay, so the learning objectives. Number one, state the constant and constant multiple and power rules. Two, apply the sum and difference rules to combine derivatives. Use the product rule for finding the derivative of a product of functions. Use the quotient rule for finding the derivative of a quotient of functions. Extend the power rule to functions with negative exponents. And then finally, combine the differentiation rules to find the derivative of a polynomial or rational function. Okay, so we're going to be able to find derivatives of, somewhat very complicated functions, actually. So let's go ahead and start reading. It says, finding derivatives of functions by using the definition of the derivative can be a lengthy and, for certain functions, a rather challenging process. For example, we previously found that the derivative of the square root of x with respect to x was 1/2 square root of x. By using a process that involved multiplying by an expression by a conjugate prior to evaluating the limit. The process that we could use to evaluate d dx, the derivative of the third root of x, using the definition, while similar, is more complicated. In this section, we develop rules for finding derivatives that allow us to bypass this process. We begin with the basics. Okay, so yeah, in this section, we are going to learn how to take this derivative that we've done before in, it took us, maybe a couple minutes before. It's going to take us now a few seconds to be able to compute this derivative. And this derivative here, as it mentions, it is more complicated than the one highlighted in yellow, but we will be able to do it in a matter of, like 10 seconds once we learn these differentiation rules. So we start with the basic rules. Let's read. The functions f of x equals c and g of x equals x to the n, where n is a positive integer, are the building blocks from which all polynomial and rational functions are constructed. To find derivatives of polynomials and rational functions efficiently, without resorting to the limit definition of the derivative, we must first develop formulas for differentiating these basic functions. So the basic functions that we're going to look at are the constant function and the basic power function here, where n is a positive integer. Okay, so the constant rule. We first apply the limit definition of the derivative to find the derivative of the constant function f of x equals c. So, I could ask you to find what's the derivative of f of x equals 5, a constant 5, or f of x equals a constant 7, or f of x equals a constant 9. And, each of these would take some time. If you use the limit definition of the derivative. But notice that we can do this in general for just f of x equals c, and let's see what the derivative of this would be. For this function, both f of x equals c and f of x plus h equals c. So we obtain the following result. The derivative is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. That's just a reminder of the derivative, the limit definition. But both of the quantities in the numerator are c. So we get c minus c, which is 0, and 0 divided by h is 0, and the limit as h approaches 0 of a constant 0 is 0. And so notice that basically the derivative function of a constant function is 0. So let's continue reading. The rule for differentiating constant functions is called the constant rule. It states that the derivative of a constant function is 0. That is, since a constant function is a horizontal line, the slope, or the rate of change, of a constant function is 0. We restate this rule in the following theorem. Okay, so it kind of talked about it there in terms of the graph of the function. The graph of a constant function is a horizontal line. And yeah, we know that the derivative function should give us the slopes of the tangent lines. Well, if it's a horizontal line, the slope of the tangent line is 0. Therefore, the derivative function must return 0 always. And that's why the derivative of a constant function is the 0 function. So theorem 3.2, let C be any constant. If f of x equals c, then f prime of c equals 0. And actually, that's a typo there. It should say then f prime of x equals 0. Okay, so that's now specifically f prime of c is also 0, but the statement in black above is better because it says that the derivative at any x value is equal to 0. Alternatively, we may express this rule as the derivative with respect to x of the constant function c is equal to 0. Okay, very good. So apply the constant rule. Earlier we said, we could use the limit definition here, limit definition there, limit definition here. But we've just found in general that for any function that is a constant function like f of x equals 8, the derivative of this function f prime of x is equal to 0. And that's it. It takes, 1 second to write that down. So solution, this is just a one-step application of the rule. And we're done. Right, notice we didn't have to use the limit definition because we already did it over here in general and kind of proved a theorem about constant functions. So let's take a look at the next one here, the power rule. We have shown that the derivative of x squared is equal to 2x. And the derivative with respect to x of x to the 1/2 is 1/2 times x to the negative 1/2. At this point, you might see a pattern beginning to develop for derivatives of the form d dx of x to the n. We continue our examination of derivative formulas by differentiating power functions of the form f of x equals x to the n, where n is a positive integer. We develop formulas for derivatives of this type of functions in stages, beginning with positive integer powers before stating and providing or proving the general rule for derivatives of functions of this form. We take a look at a specific case, d dx of x cubed. As we go through this derivation, note that the technique used in this case is essentially the same as the technique used to prove the general case. Okay, so let's take a look at the derivative here. And since it's given here, I'll just write it all out. That way we don't, sometimes it's easier to see it actually being written out. So we're going to do the limit as h approaches 0 of f of x plus h minus f of x. And this is divided by h. Here, f of x, we are taking to be x cubed. So f of x plus h is going to be x plus h cubed, which we can work out. Let's see, they work it all out there. They don't really show the work, but this is x plus h times x plus h times x plus h. And there is a shortcut for this, but I'll multiply the first two and get x squared plus 2xh plus h squared. That's just multiplying here, 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 and here. And then we have this times the third factor of x plus h. And then we multiply here, we get x cubed plus x squared h plus 2x squared h plus 2xh squared plus xh squared plus h cubed. And so this actually simplifies to, let's see here, we have an x squared h and a 2x squared h. And so that would be x cubed plus 3x squared h plus, and then xh squared plus 2xh squared is 3xh squared plus h cubed. Okay, so now we're ready. We have f of x plus h here. And we can plug into our limit. The limit as h approaches 0 of f of x plus h, that is x cubed, plus 3x squared, h plus 3x h squared, plus h cubed, minus f of x. F of x is x cubed divided by h. Okay, so then we can simplify this. This is a limit as h approaches 0. X cubed, of course, can cancel since there's a positive and a negative one there. And then we can factor out an h from the numerator. H factors and we get 3x squared plus 3xh plus h squared. This is divided by h. And this is the limit as h approaches 0 of, if we cancel these h's, 3x squared plus 3xh plus h squared. Now we can use direct substitution, plug in 0 for h. This is 3x squared plus 3x times 0 plus 0 squared. You can see that the last two terms become 0. And so this is f prime of x. And we just found that f prime of x, the derivative function is 3x squared when f of x is equal to x cubed. Okay, so there's all that work. Showing the steps. And so let's see here. Let's kind of jump down a little bit. If f of x is equal to x cubed, then f prime of x ended up being, so this exponent kind of came down here and we got 3x, and then we subtracted one from the exponent, and that's where we got our 3x squared from. Well, this is a pattern that we might be noticing. So let's read here this paragraph. It says, as we shall see, the procedure for finding the derivative of the general form f of x equals x to the n is very similar. Although it is often unwise to draw general conclusions from specific examples, we note that when we differentiate f of x equals x cubed, the power on the x becomes the coefficient of x squared in the derivative, and the power on x in the derivative decreases by 1. The following theorem states that the power rule holds for all positive integer powers of x. We will eventually extend this result to negative integer powers. Later, we will see that this rule may also be extended to rational powers of x, and then to arbitrary powers of x. Be aware, however, that this rule does not apply to functions in which a constant is raised to a variable power, such as 3 to the x. So it is important. This rule does not apply to exponential functions, right? That's what that kind of function is. This rule only applies to, these are called power functions, when the variable is the base and then the exponent is a constant. Okay, so here's the power rule, and this is a very powerful rule. Let n be a positive integer if our function is a power function, like f of x equals x to the n, then the derivative f prime of x is just going to be the exponent n, the original exponent n, times x raised to the n, but we subtract 1. Alternatively, yeah, you can express this as d dx, the derivative with respect to x of x to the n. And this is just n times x to the n minus 1. Now we have a proof here for this theorem, theorem 3.3, but we won't really go through the proof in detail. It uses the binomial theorem, yeah, so we'll skip this proof here, but I'm sure most of everybody will essentially just believe that this is true, that it can be proven. And if you'd like to go over the proof, feel free to visit me during my office hours. Okay, so yes, it can be proven. It does work. All right, so applying the power rule. So it's very, oh my gosh, look at this. F of x equals x to the 10th. This would be very difficult to do with the limit definition. Finding the derivative with the limit definition, but with the power rule, it's the derivative f prime of x is going to be, we bring the exponent to the front, basically, x, and then we just subtract 1 from the exponent. The exponent was 10. Now it is 10 minus 1. So this is 10 to the x, 10 times x to the 9th. This is the derivative function here. F prime of x equals 10 x to the 9th. So you can basically do these, in 1 second. Okay. You can try this one on your own here. Think about it for 5 seconds and then write down the derivative. You should get f prime of x equals 7x to the 6th. All right. So notice how fast we can do them now. Again, also x to the 7th, this would take pretty long time. As you see that, we did the derivative earlier of x cubed. Here's all the work, right? But just using the power rule, x to the 3rd. Okay, well, we kind of bring the exponent down, x, subtract 1 from the exponent, and we're done. Right, notice how fast that is compared to all of this work that we did before, all of this prep work that we had to do just to start the limit definition. This is way faster. But of course, this all relies on the limit definition. Okay, next. Well, sometimes you don't want to take the derivative of a single function, but maybe a sum of 2 functions, or a difference of 2 functions, or a constant multiple of a function. So let's read. We find our next differentiation rules by looking at derivatives of sums, differences, and constant multiples of functions. Just as when we work with functions, there are rules that make it easier to find derivatives of functions that we add, subtract, or multiply by a constant. These rules are summarized in the following theorem. So theorem 3.4, sum, difference, and constant multiple rules. So let f of x and g of x be differentiable functions and k be a constant. Then each of the following equations hold. Sum rule. The derivative of the sum of a function f and a function g is the same as the sum of the derivative of f and the derivative of g. Okay, so basically, what is this saying here? Well, let's go ahead and say this. Well, we'll do an example here. Let's say we have a function, and let's call this function h of x. H of x is equal to, we just did x cubed, and then a moment ago, I believe x squared, the derivative of x squared was shown. So h of x is written as, x cubed plus x squared. That's a perfectly legitimate function. But we could think of h of x as the sum of 2 functions, f of x and g of x, where f of x is equal to x cubed and g of x is equal to x squared. Okay, so this sum rule says if you want the derivative of h of x, well, this is just going to be the derivative of f of x plus the derivative of g of x. So if you can find the derivative of these simpler pieces of h of x, so f prime of x, we can find that. Yes, we can, because we did it earlier. And the derivative of g of x that was given earlier, and you can actually do it right now with the power rule, is just 2x to the 1, or 2x. And so the derivative of h of x, called h prime of x, is equal to the derivative of f plus the derivative of g. And notice we just took the derivative of a more complicated function that had multiple terms by just taking basically the derivative of each individual term. The difference rule essentially says the exact same thing, but for subtraction of 2 functions. So if you have a function j of x, where j of x is the difference of 2 functions, f of x and g of x, then what is the derivative of j of x? It's just going to be the difference of the derivatives of f and the derivative of g. Okay, what about a constant multiple rule? Well, what if we have a function, again, we're going to use, let's use f of x from before. F of x was equal to x cubed. Right, so what if I want to find the derivative of f of x equals x cubed? Or I'm sorry, not f of x equals x cubed. We know how to find that. We know that the derivative of f of x is f prime of x, which is equal to 3x squared. But what if we created a new function, and let's call this function g of x. And g of x is going to be a constant, I'll call it 5 times f of x, which is 5x cubed, right? Because f of x is x cubed. Now, how do we find g prime of x? How do we find the derivative of g, which is a constant multiple of f? Well, that would be unfortunate if we had to use the limit definition, because that would be a lot of work. It can be done that way, but it would be a lot of work, as it was earlier when we did the derivative of x cubed. This constant multiple rule says, well, you can actually just say the derivative of g of x, g prime of x, is going to be just the constant 5 times the derivative of f. And so this is just going to be 5 times the derivative of f is 3x squared. And so this is just 15x squared, and we're done. There's the derivative of a constant multiple. And this worked for any constant. If the constant was 6, well, then we can take the derivative of the function f of x and then multiply it by the constant afterwards. Okay, so we have a proof. And again, excuse me, we won't cover the proof in detail. You can come see me if you would like to go over the proof. All right. I do like going over proofs, but they do take a lot of time, and most people generally are okay without seeing it. Okay, so applying the constant multiple rule. Ooh, let's see. Find the derivative of g of x equals 3x squared, and compare it to the derivative of f of x equals x squared. So g of x, well, let's see here. What is the derivative of 3x squared? According to my constant multiple rule that we saw earlier, it was a little bit above, we can think of this as 3 times, and I'll put it in parentheses, x squared. Right? G of x is 3 times x squared. And if we think of x squared as another function, f of x, then to take the derivative, and the derivative here is going to be, I'm going to do d dx of g of x. The derivative of that function is the derivative of 3x squared. But according to the constant multiple rule, this constant of 3 can essentially be, kind of ignored, and we take the derivative of only that function, x squared. The derivative of x squared is going to be, we know that that is actually 2x. And so what is this product here? We end up getting 6x as g prime of x. G prime of x is equal to 6x. Now, how does this compare to the derivative of f of x? F of x is given, way up here. Now, f prime of x is equal to 2x. And how does g prime compare to f prime? We see that g prime of x is equal to 3 times 2x. It's 3 times more. This is 3 times f prime of x. Well, if Okay, so we're saying g prime of x is equal to 3 times f prime of x, but g of x was equal to 3 times x squared to begin with. So g of x was initially 3 times f of x. So then when we took the derivative, I'm going to put a little prime here. When we took the derivative of the left side, we took the derivative of the right side. And basically, this tells us that when we take the derivative of a function, we can kind of ignore a constant multiple and just take the derivative of the function, the part that has the x in it. So let's go ahead and read here. So it says, since f of x equals x squared has a derivative of f prime of x equals 2x, we see that the derivative of g of x is 3 times the derivative of f of x. This relationship is illustrated in figure 3.18. Yeah, and so you see 3x squared is kind of a parabola that rises faster. And so its tangent lines, and not only does it rise faster, but it rises 3 times faster. So then its tangent lines are going to have slopes that are 3 times greater than the slopes of the tangent lines of f. Okay. All right, so how do we apply these basic derivative rules? So we have a few rules that we've already gone over. If we have a function f of x equals 2x to the 5th plus 7, the derivative, so I'm going to apply the derivative d dx to my function f of x. This is going to give me the derivative function. Once this is done, I'm going to derive both the left and the right hand side of this equation. So on the left-hand side, I'm going to just get f prime of x, which is the derivative function notation. On the right-hand side, well, how do we take the derivative of a sum of two functions? We said earlier that this is just the derivative of the first function, 2x to the 5th, plus the derivative of the second function. Wait a minute, there is a constant that is multiplying. There's a constant multiple in the first function. So I can write this as, I'm going to kind of factor out the 2 essentially from the derivative. I write 2 times the derivative of x to the 5th plus the derivative with respect to x of a constant 7. And so what is this equal to? I'm going to slide this up just for a moment. This is equal to 2 times, and then the derivative of x to the 5th is using the power rule, that's 5x to the 4th, plus the derivative of a constant is 0. So this is now 10x to the 4th. F prime, and let's see here, f of x is 2x to the 5th plus 7. F prime of x is equal to 10x to the 4th. And so you might start noticing here that, wait a minute, that's just kind of like bringing down the exponent, multiplying the 5 with a 2, that becomes the coefficient, and then subtracting 1 from the exponent gives us the new exponent of the derivative. That's the power rule. And then a constant's derivative is 0, so that kind of went away. And so that's why we have our derivative of f of x, f prime of x. All right. All right. So finding the equation of a tangent line. Well, we've done this in the past, but now it should be a little bit easier because we have a quicker way to find the derivative. So this example, 3.22, asks us to find the equation of the line tangent to the graph of f of x equals x squared minus 4x plus 6 at x equals 1. So what do we need to do? To find the tangent line, we need to find basically y equals mx x plus b, or y minus y1 equals m times x minus x1. And we'll use the point slope form. This m here is going to be the slope of the tangent line that we talked about before. The slope of the tangent line can be found by finding the derivative function. So let's go ahead and find the derivative function. If my function f of x is equal to x squared minus 4x, and I believe this has dropped the using all those derivative rules or showing all the steps. I'm going to show it one more time, but basically we take the derivative, and this is the notation on the left hand side, and then so we take the derivative on the right hand side. So we're taking the derivative on the left hand side. That's just the derivative of f of x is called f prime of x, so we'll put our correct notation, and then we'll apply the derivative d dx to x squared, right? Each of these functions, there's three terms to this quadratic function, but you can think of them each as individual functions. So we'll apply to negative 4x to the 6. Okay, so well, let's take a look here. So f prime of x is going to be equal to the derivative of x squared is 2x. The derivative here, and the second term, we technically need one more step. We can apply the constant multiple rule to take out that negative 4, and then we will apply the derivative to just x to the first power. And then the derivative of a constant, we can take this one right away. That's 0. And so what is the derivative? What is the derivative d dx of x to the first power? According to the power rule, we kind of bring down the exponent. That's going to be 1 times x raised to the 0, because we subtract 1 from the exponent. And 1x to the 0, that's just 1. So in general, the derivative of a function like 1x is just going to be the coefficient 1. And so our derivative function f prime of x is now 2x minus 4. The derivative of x we said was 1 plus 0. And so we have our simplified derivative here, 2x minus 4. So we want the derivative, we want the slope of the tangent line when x is equal to 1. So we want to find f prime of 1, and this is 2 times 1 minus 4. 2 minus 4 is negative 2. So the slope of the tangent line is negative 2. Okay, we're going to need this for our line. And now we need a point on our line. Since this needs to be at x equals 1, then we should find the y value corresponding to x equals 1. So we'll plug in 1 to the function. And so we get 1 minus 4 plus 6. This is equal to 6 minus 4 is 2 plus 1 is 3. And so we have our point 1 comma 3. This is our x1, y1, if you want to think of it that way. And so now we can just use our point slope form and plug everything right in. Y minus y1 is 3 equals the slope of the tangent line, which is negative 2, times x minus x1, which is 1. So here we have y minus 3 equals negative 2x plus 2. And if we add 3 to both sides, we have our negative 2x plus 5. That is the equation of our tangent line. And then let's go ahead and take a look at this. X squared minus 4x plus 6. X squared minus 4x plus 6. Desmos. X squared minus 4x plus 6. And if I can remember correctly, I believe it was y equals 2x plus 5. No. Let's go ahead and go back and check. negative 2x plus 5. So we can add a negative sign there. And bam. Yes, our line is tangent. You can see, yes, it just grazes that parabola at x equals 1. All right, and if you zoom in a lot, I mean, it's pretty cool just to see that. When you zoom in so much, the parabola is basically locally, you can say it's linear. It looks almost identical to this line when you zoom in. And if you zoom in even further, it looks even more like that line, right? You can't even tell the difference between the parabola and the line anymore, because when you zoom in enough, they're basically both looking linear. Of course, the line is linear, but the parabola has a, it's got curvature to it. But when you zoom in enough, and that's why the tangent line is a good approximation of the curve for certain x values. Okay. All right, very good. Next, we have the product rule. Okay, so the product rule is basically how to take the derivative of a product of two functions. And it turns out it's not going to be as simple as the sum rule, where, oh, if you have a sum of functions or a difference of functions, like we did in this, we had x squared minus 4x and then plus 6. We can just say, okay, well, that's going to be the derivative of x squared minus the derivative of 4x plus the derivative of 6. We can just break it up that way. With the product rule, it's going to be a little bit, trickier, but not too difficult. So let's read. Now that we have examined the basic rules, we can begin looking at some of the more advanced rules. The first one examines the derivative of the product of two functions. Although it might be tempting to assume that the derivative of the product is the product of the derivatives, similar to the sum and difference rules, the product rule does not follow this pattern. To see why we cannot use this pattern, consider the function f of x equals x squared, whose derivative is f prime of x equals 2x, and not d dx of x times d dx of x. So yeah, just to kind of explain that one more time, f of x equals x squared. This is x times x, right? So we know that the derivative f prime of x is equal to 2x. Now, could we just say, well, this is just, since this is x times x, could we just say, let's take the derivative of the first function, the derivative of the second function, and just multiply those two? And would that be the derivative of the product of x and x? And you see that the derivative of x, we said earlier, was 1, and the derivative of x, again, is 1. And so notice this is 1, which is not equal to 2x. So no, you can't split this up into a product like x times x and then take the derivative of each of the individual factors and then multiply them. That doesn't work. So let's go ahead and take a look at the theorem 3.5, the product rule. Let f of x and g of x be differentiable functions. Then the derivative of the product of f and g is equal to the derivative of f times the function g plus the derivative of g of x times the function f. And the way I like to write it is like this. F times g, so here's our function, the product of f and g, and we use the prime notation to denote that we are taking the derivative of this. And this is f prime times g plus g prime times f. And some students have kind of called this fig, kind of looks like fig plus gif, right? So you can think of it that way if you'd like. So f prime times g plus g prime times f. Okay. There are many notations for it, right? So we have basically here's the same notation, except we have, each of them are written as a function of x. So let's go ahead and read. This means that the derivative of a product of two functions is the derivative of the first function times the second function plus the derivative of the second function times the first function. Okay, so fig gif. Now, this is a very interesting proof here. And I like this proof, but again, we won't go through it because, well, it can be proven using the limit definition, but we will kind of skip that for now. If you'd like to, go over this proof again, as usual, come see me in my office. There's a pretty cool trick that they use in this proof. So applying the product rule to functions at a point. Okay, so let's go ahead and try to apply the product rule. Well, what are we given here? We are told that j of x, we're defining a function j of x, and j of x is defined to be the product of some function f of x and g of x. And so we want to find j prime of 2. Okay, well, if we want to take the derivative of j, that's going to be j prime of x. And according to the product rule, I'm going to write here a middle step, the derivative, if I want to take the derivative of the right-hand side, which is a product of two functions, f of x times g of x, then this is going to be equal to the first derivative of the derivative of the first function, f prime of x, times g of x, plus g prime of x, the derivative of the second function, times the first of the functions, f of x. This is j prime of x. So if we want to find j prime specifically of the value 2, then we can just evaluate each of these at 2. And now for this problem here, we were given what these values are. So, I mean, I can highlight them above. F of 2 we know, f prime of 2 we know, g of 2, and g prime of 2. So we can just plug in. F of 2 is, or f prime of 2 is the first one, that is -4, times g of 2, which is 1, plus g prime of 2, which is 6, and f of 2, which is 3. So you can combine those values there, you get 14 as your j prime of 2. So the slope of the tangent line when x is equal to 2 for this product, for this function of, which is a product of two functions, is 14. Okay, so that's all we're asked to do there. Now, there are multiple ways to do some of these problems sometimes. So here we're given in example 3.2.4, we're given a function, again, we're calling it j of x. And this function is the product of two functions. Let's call these functions f of x equals x squared plus 2, and g of x is equal to 3x cubed minus 5x. So the derivative f prime of x, we can find, that's pretty easy. We'll use the power rule, that is 2x plus the constant 2, its derivative 0, so it goes away. And the derivative g prime of x is going to be, here we're going to use the power rule and the constant multiple rule at the same time. And so we get 9x squared minus 5x is derivative is 5. So we have minus 5. So what is the j of x is defined to be, it is f of x times g of x. So if we want the derivative of j of x, we want j prime of x. According to the product rule, this is going to be f prime of x times g of x. Fig plus gif. And so we plug in our functions. F prime is 2x. G of x is 3x cubed minus 5x. plus g prime of x, which is 9x squared minus 5. And I need just a little bit of room here. Times f of x, which is x squared plus 2. This is j prime of x. This is our derivative. Now, could we have done this problem a little bit differently? The answer is yes. So yeah, we can check our answer there. It looks like the answer is correct. Now, if we multiply it here, let's kind of multiply some of this stuff out here, and we'll distribute the 2x. And then we will distribute the other terms as well. So we can also write j prime of x as, I'm going to distribute the 2x and get 6x to the 4th minus 10x squared plus, then I'll distribute here, 9x squared times x squared is 9x to the 4th. 9x squared times a positive 2 is positive 18x squared. Minus 5 times x squared is minus 5x squared. And minus 5 times positive 2 is minus 10. If we combine like terms, then we have 15x to the 4th. That's those two terms. Plus 8x squared. That's these two terms. Oh, not 8x squared. There's a minus 5x squared as well. So we should combine that at the same time. That would give us, instead of 8x squared, a 3x squared. And then minus 10. So here is our simplified derivative function. I mean, we could have officially stopped when we had this as our derivative function. They both count as derivative functions. The reason that we multiplied it out was because we want to look at an alternative solution for this problem. Because you may have noticed that I could just multiply these binomials together and get a different form for j of x. Right, if we multiply together, we get 3x to the 5th. Multiply here, and that gives me a minus 5x to the 3rd. Then we multiply here, and that gives us a positive 6x cubed. And then finally, minus 10x. And if we take the derivative here, j prime of x, this is going to be, okay, we bring the exponent here. 5 times 3 is 15. Subtract 1 from the exponent, that gives us an exponent of 4. Minus 5 times a 3 is a minus 15. X, subtract 1 from the exponent, plus 3 times 6 is 18. X, subtract 1 from the exponent, and we get an exponent of 2, minus, here we'll do 10. X to the 0, which x to the 0 is just 1, so we can leave it off. And so j prime of x, after combining these two middle terms, gives us 15x to the 4th plus 3x squared minus 10. And so wait a minute, that is exactly what we got before. So, you know, in this case, for this problem, we could, since j of x is defined to be the product of two functions, in this case, these two functions are both binomials, there's two ways to solve this problem. And they would be, one way would be to use the product rule. The other way would be to multiply the two functions together, the two binomials together. Then we have, you know, just a sum and difference of functions, and so we don't have to use the product rule anymore. Then we just take the derivative, and we would get the same thing. Now, this might look easier in this case, and it is in this case, but sometimes we have two functions where you can't multiply them out. Like, let's say j of x was defined to be, let's say, well, what could we use? Something like x cubed minus 5 raised to the 8th power times 3x squared minus or plus 7 raised to the second power. Evaluating, multiplying this out would take forever because of that exponent of 8. We'd have to multiply x cubed minus 5 a bunch of times, and so it'd take a long time. And in this case, for this function, it would actually just be easier to use the product rule. So we should know how to do it both ways. And then over time, we'll figure out which one is the most efficient in, depending on, each case. Okay. Yeah, and so it does say to check, we see that j of x, if you multiply it all out, that's what we ended up getting. They put 3x to the fifth plus x cubed minus 10x. That's essentially what we had here, 3x to the fifth. If you combine these two x cubes, that is technically positive x cubed, and then a minus 10x. The derivative ended up coming out to the same thing when you did it either way, right? So there's two ways to do this problem. Okay, the quotient rule. Having developed and practiced the product rule, we now consider differentiating quotients of functions. As we see in the following theorem, the derivative of the quotient is not the quotient of the derivatives. Rather, it is the derivative of the function in the numerator times the function in the denominator minus the derivative of the function in the denominator times the function in the numerator, all divided by the square of the function in the denominator. In order to better grasp why we cannot simply take a quotient of the derivatives, keep in mind that, and so they give another counter example here. So if you have the function, x squared, how can we take the derivative of x squared? Well, could we think of x squared as x cubed over x? The answer is yes. X cubed over x for all non-zero values is equal to x squared. And so, okay, well, if we want to take the derivative of this quotient of x cubed over x, could we just take the derivative of the top function, x cubed, and then divide that by the derivative of x? And this is, well, we know that the derivative of x cubed is 3x squared. The derivative of x is 1, so we have a derivative in the end of 3x squared if we did it this way. But wait a minute. We know that the derivative of x squared is 2x, which is not equal to 3x squared. So something over here is wrong, and it's because the derivative of a quotient of two functions is not the quotient of the derivatives of the individual functions. So we can give our notation for this. It's basically given here, but if you have f over g, and we're going to put the prime to indicate we're taking a derivative, the derivative of a quotient of two functions, f and g, is still fig gif, but now it's a minus sign instead of a plus like in the product rule. We have a minus sign, and we also need to divide by g squared. And so my notation here is like I'm writing it more simply, but basically it's, if j of x is f of x over g of x, then exactly what I wrote, the derivative f of x divided by g of x, the derivative of this is equal to the fig f prime times g minus gif g prime times f over g squared. Okay, so however you want to write it, and you can also use the d dx notation. This is f prime here times g minus g prime times f all over g of x squared. The proof of the quotient rule is very similar to the proof of the product rule, so it is omitted here. Instead, we apply this new rule for finding derivatives in the next example. All right. So let's go ahead and take a look at k of x here. So we're going to think of k of x as a quotient of two functions, f of x over g of x. And this f of x then, that means that the top function is going to be called f of x. The bottom function will be called g of x. And because the product rule or the quotient rule uses f prime of x and g prime of x, let's find f prime of x. F prime of x, if f of x is 5x squared, f prime is 10x. If g of x is 4x plus 3, g prime of x is 4. And so according to the quotient rule, k prime of x is equal to f prime of x times g of x minus g prime of x times f of x all over g of x squared. So let's just plug in. We have all of these functions now. This is f prime of x, which is 10x, times g of x, which is 4x plus 3, minus g prime of x, which is 4, times f of x, which is 5x squared. This is all divided by the function g, 4x plus 3, and this function should be squared. And so now we can try simplifying a little bit. We can look ahead and see if anything's going to simplify. Not so much, but let's go ahead and multiply it out. Here we have 40x squared plus 30x minus 20x squared all over the denominator 4x plus 3, that function squared. And so the only thing that we can really cancel here is 40x squared minus 20x squared, that's 20x squared plus 30x. This is all over 4x plus 3 squared. Doesn't really simplify much more than that. And yes, this is k prime of x. Or if, yeah, I mean, we'll leave it as k prime of x. All right, very good. So the extended power rule says it is now possible to use the quotient rule to extend the power rule to find derivatives of functions of the form x to the k, where k is a negative integer. And so before we could only, officially, we could only find the derivative of, let's say, f of x equals x to the 5th, or g of x equals x to the 13th, right? The derivative of this was 13x to the 12th. But what about if, let's say, h of x was x to the negative 7th power? What do we do in this case? It turns out that the power rule that we knew from before still works. It's just we couldn't prove it before. So that's why it was only given for positive integers, because it couldn't be proven before. But now we're going to prove in just a moment that the derivative of this type of function is just going to be the, we kind of bring the exponent down, negative 7 times x to the negative 7 minus 1, or negative 7 x to the negative 8. Right, so that is our derivative function. It works in the exact same way. It basically is just saying it works for negative integers as well. Now we can prove this because if x is raised to a negative integer, like h of x is here, if h of x is x raised to a negative integer, then that negative integer that's raising the negative exponent there, we can write it as 1 over x to the 7th here. And now we can use the quotient rule to take the derivative of this h of x function, and we would end up seeing that it does come out to be h prime of x is equal to -7x to the -8th. And you could say, well, does this pattern always work? And the answer is yes. The proof for it is right here. And so this works every time. Okay, again, we'll skip the proof. So using this extended power rule, so if f of x is equal to x to the -4th, then the derivative, if we apply the derivative to both sides, on the left-hand side, the derivative notation of f of x is f prime of x. On the right-hand side, essentially we bring the exponent down, x raised to the -4 minus 1. So f prime of x is equal to -4x to the -5th power. And we are done. This problem would be quite a bit more difficult using that limit definition. Notice we haven't really talked about the limit definition anymore because these derivative rules are going to essentially make that limit definition obsolete for a good while. Okay, so combining some of these rules here. So use the extended power rule and the constant multiple rule to find the derivative of this function f of x. And so there's actually two ways. A lot of times there's multiple ways to do these problems. So that's always fun. So the first way that I'll show is, I'll show maybe the more complicated way. And so we could think of this function, and I'm going to call it for right now, I'll call it k of x. Let's just kind of ignore this for a second. We already did the solution to this one up above. So k of x is equal to 6 over x squared. And remember, this is a quotient of two functions, so we can think of this as f of x over g of x. And that means that my function f of x, we are taking to be 6. My function g of x is going to be the denominator function, is x squared. And so f prime of x, the derivative of any constant we know is 0. The derivative of x squared, we've already talked about a bunch of times, that's just 2x. And so the derivative here, what is k prime of x? I'm not going to write out the formula, but it is f prime of x times g of x minus g prime of x, 2x, times f of x, 6, over g of x, which is x squared, squared. And here I'm using f fig minus gif. This is the quotient rule, right, over g squared. That's what I used here for the derivative of f over g. Okay, so I can simplify this here. 0 times x squared, that's just 0, minus, on top I'm going to have a 12x. On the bottom I'm going to have x to the 4th. And so this simplifies to -12 over x to the 3rd. If you cancel out an x, and this can be written as -12x to the -3rd, if you will. Okay, so that was the tougher way, using the quotient rule. Sometimes, if you take a close look at this function here, 6x squared, if you can write it in the form 6 times x to the -2, which in this case we can, because 6 over x squared, just in case somebody's not seeing it, this is 6 times 1 over x squared, right, or 6 over 1 times 1 over x squared, and that's just 6 times x to the -2. And now we can just use the power rule here. The derivative f prime of x is going to be, we're going to multiply this exponent times a constant. That's going to be -12, and then x raised to the -2 minus 1 is -3. And notice we have the exact same answer in basically one step. And we're done. So there are some cases where, yeah, if you notice that you can rewrite your function so that it's just a nice simple power function, it's very easy to take the derivative of it. All right, combining differentiation rules. I believe we're getting pretty close. Yep. So we will end pretty soon here. Combining differentiation rules, as we have seen throughout the examples in this section, it seldom happens that we are called on to apply just one differentiation rule to find the derivative of a given function. At this point, by combining the differentiation rules, we may find the derivatives of any polynomial or rational function. Later on, we will encounter more complex combinations of differentiation rules. A good rule of thumb to use when applying several rules is to apply the rules in reverse order in which we would evaluate the function. Okay, so let's go ahead and see what exactly this means. So we want to find the derivative of k of x. So we're told that k of x, it's kind of a complicated-ish function here. It is the sum of 3 times h of x and x squared times g of x. Okay, well, if we want to find the derivative of k of x, then we just find the derivative of the other side as well. And according to the sum rule, this is just going to be, okay, so we can do the derivative d dx of the first of these functions, 3 times h of x, plus the derivative of the product of x squared times g of x. Okay, well, the first derivative is nice and easy because you can just factor out the 3 and take the derivative, apply d dx to h of x. But then here, when we take the derivative of product, this is going to be a little bit more complicated. We're going to need the product rule. And so this is going to be the derivative of the first function. If we consider the first one to be f and the second one to be g, then we can use the product rule. F prime, the derivative of the first function, is 2x times g of x plus g prime of x times the derivative of the first function. I'm sorry, not the derivative, but times the second function, times the first function there, that is x squared. And so now we have 3 times the derivative of h of x, that can be called just h prime of x, plus 2x g of x, plus x squared times g prime of x. Now, it doesn't look like we were given any of these functions. On the left-hand side, we'll put our k prime of x, since this is the derivative of k of x. Were we given any functions? No. So this is our answer. 3 times h prime of x plus 2x times g of x plus x squared times g prime of x. So we first applied the sum rule, then the constant multiple rule, and the product rule to take the derivative of those terms. Okay, extending the product rule. So the product rule can be extended to more than 2 functions. And the way that we can do this is, okay, well, if we have a function k of x that is a product of f of x, g of x, and h of x, how can we apply the product rule if it's 3 functions? Well, we can just pretend like the first 2 functions are a single function. And so we're going to think of k of x as the product of 2 functions, where the first function is f of x times g of x, and this second function is h of x. So if we look at the derivative of k of x, the derivative of k of x is going to be the derivative of its first function. The first function we're considering to be f of x, g of x. And we have the derivative of that. Right? We take the derivative of the first function times the second function, h of x, plus the derivative of the second function, the derivative of h of x, times the first function. The first function was actually the product of 2 functions, f of x, g of x. And so notice here, we haven't really bypassed anything because, well, now one of our derivatives here is going to require the product rule itself. And so if we have multiple functions that are being multiplied together, then we're just going to apply the product rule multiple times. The derivative of f of x times g of x, here we need to apply the product rule. This is f prime of x times g of x plus g prime of x times f of x. This is the derivative of the product of f and g. So then there's an h of x multiplying the outside of it. And then we have plus the derivative of h of x is h prime of x times f of x times g of x. Can this be simplified? Yeah, I guess so. Let's go ahead and distribute our h of x to both of these terms here. And so we have, let's put them in alphabetic order, f prime of x times g of x times h of x plus f of x times g prime of x times h of x plus f of x times g of x times h prime of x. And this is our derivative function if we have more than two factors. Whew. All right, and that's exactly what our answer is. So what if we need to somehow combine the quotient and product rules, right? Functions can be very complicated. So we have a function here, which is h of x, which is, okay, it's a quotient. In the denominator, we have 3x plus 2. That's a function. But in the numerator, notice we have 2x cubed times some other function, k of x. Now, we're not given what k of x is, but we have a product of two functions in the numerator. Okay, so my function technically here, if we want to think of this as f of x over g of x, f of x is 2x cubed times k of x. G of x is a nice simple function, 3x plus 2. So we can find g prime of x pretty easily. That is just 3. But what about f prime of x? Well, since f of x is a product of two functions, the derivative is going to require the product rule. So the derivative here is going to be the derivative of the first function, which is 6x squared times the second function, k of x, plus the derivative of the second function, the derivative of k is k prime of x, times the first function, 2x cubed. So notice, yeah, we needed the derivative of f. We needed to use the product rule. We haven't even really started deriving h of x. Now, h prime of x, the derivative of h, if we start deriving it now, according to the quotient rule, is fig, and I'm going to use a shorthand notation here, fig minus gif over g squared. Well, we have all of these functions now. F prime, we just found, is 6x squared k of x plus k prime of x times 2x cubed. And this f prime should be multiplied by g. G is 3x plus 2. And notice, yeah, these problems are getting longer. A little bit longer. That's okay. Minus g prime is 3 times f, and f was 2x cubed times k of x. This is all over g squared. G is 3x plus 2 squared. Now, is this what we have in the answer? Basically, yes, that is this step here. And then we can do a little bit of simplification, but I will leave it there. It doesn't simplify too much, so you can distribute. Basically, they just distributed these terms here, and then combining in like terms. I mean, also distributing here. It won't cancel too much. Doesn't simplify that much. All right, so example 3.31. What else can we do with these differentiation rules? Well, can we determine the values of x for which f of x equals x cubed minus 7x squared plus 8x plus 1 has a horizontal tangent line? So where does a function have a horizontal tangent line? And we can actually answer this by just looking at the graph here. The horizontal tangent line is a tangent line whose slope is 0. So when the slope of the tangent line is 0, the function has a horizontal tangent line. While the slope of the tangent line is the value of the derivative function. So whenever that derivative function has a value of 0 is where we have our horizontal tangent line. So let's find the derivative function f prime of x. F prime of x is 3x squared minus 14x plus 8 plus 0, right? The derivative of the 1 goes away. And so now we have this as our derivative function. We want to know, where is this function 0? So we set it equal to 0 essentially. And then we can factor this here. It's going to take me a moment to factor. 8 times 3 is 24. Two numbers that multiply to 24 and add up to negative 14 are negative 12 and negative 3. And so if we do x minus 12 times x minus 3, divide both by 3. Oh, not 3. Why is that 3? Negative 12 times 3 is not 24. That should be a 2, of course. Negative 2, right? Those negative 2 and negative 12 multiply to positive 24 and add up to negative 14. And so our factorization is x minus 4 times 3x minus 2. And so x minus 4 times 3x minus 2. Using the zero product property, we can set each factor equal to 0. X minus 4 equals 0. 3x minus 2 equals 0. So x is equal to 4, or x is equal to 2/3. So these are the two locations where the derivative function f prime of x is equal to 0, right? For x equals 2/3 or x equals 4. And they actually give us the graph of this function in the textbook, which is nice. And we can see at x equals 4, and then x equals roughly, 2/3, 0.66. All right. Very nice. So, I mean, that really had not much to do with the derivative rules, but it's, a calculus problem where you need to find the derivative. And finding the derivative of this using the limit definition, as I've mentioned multiple times, would be very difficult. And now that we have those differentiation rules, we don't really need to use the limit definition anymore. Okay, so I believe this is the last example, yes. So the last one here, finding velocity. So we're given a position of an object on a coordinate axis at time t, and that's given by the function s of t. So this is a position function. what is the initial velocity of the object? So what is the initial velocity of the object? Okay. So let's go ahead and, so the position function, if we take the derivative, this is a function of time, so we're going to take the derivative with respect to t. The derivative of the position function gives us the velocity function. Okay, so the derivative of the position function is the velocity function. And so let's go ahead and take the derivative. The derivative of s of t, let's think of s of t. This is a rational function, t over t squared plus 1. And so we can think of it as f of t over g of t. So we're going to need the quotient rule here. Our function f is just t. Our function g on the bottom is t squared plus 1. So the derivative of, I'm getting ahead of myself here, kind of, but we should recognize that for the derivative s prime of t, this is going to be f prime times g minus g prime times f over g squared. Officially, I should be putting the t's there, f prime of t, g of t, minus g prime of t, f of t, over g of t squared, right? There's a lot of t's there, and so, okay, so let's figure out what f prime and g prime are because we need them. So f prime of t, that's equal to just 1. And this is just t to the first power, that's 1 times t to the 0, which is 1. G prime of t is equal to 2t. The constant 1 has a derivative 0. And so s prime of t is equal to, we plug all of this stuff in, f prime times g minus g prime times f all over g squared, t squared plus 1 squared. We can simplify this a little bit. The numerator is not too complicated. It is just, so I'll write it up above. The numerator is t squared plus 1 minus 2t squared. And so notice we're going to be able to combine those t squareds to get negative t squared plus 1 over t squared plus 1 squared. This is our derivative function, which can be written as just v of t, because this is now a velocity function. And so we wanted to find the initial velocity of the object. The initial velocity of this object is just going to be, evaluating this function at 0. That would be negative 0 squared plus 1 over 0 squared plus 1 squared. And this is 1 over 1, which is 1. The initial velocity is 1. It didn't give us any units, so we will leave it just at 1, maybe meters per second or whatever. The units don't really matter in this problem because we weren't given any. All right, so that is the end of section 3.3, derivative or differentiation rules. And so, we can try some exercises now. All right, well, hope you enjoyed that video, and I'll see you in the next one.